So our last video lesson was on entropy, calorimetry. We talked about enthalpy and Gibbs free energy. And we also looked at some energy diagrams. I want to just remind you again with entropy before we move on to equilibrium. I want to remind you that entropy is the measure of disorder in the system. So if you compare the three main states of matter that we see daily, solid, liquid, and gas, notice as you move towards the gas phase, you're getting higher disorder. So that would represent a system with high entropy. I'm going to put a link on Edmodo that has a really, really good explanation of entropy. If any of you want to view that, it would be, I feel like, a very beneficial to you. Solids have a very low entropy. So this is a low entropy situation because it's very orderly, and gases are very high entropy. All right. So I want to introduce you to chemical equilibrium today. Equilibrium reactions are reversible reactions. That's what they're also known as. And we represent an equilibrium state with the arrows pointing in opposite directions in the place you would normally see your yield sign. The definition of an equilibrium reaction is when the rate of the forward reaction is equal to the rate of the reverse reaction. So when the rate of the forward reaction, as you have your reactants forming your products, at some point in time during the reaction, the products can start to build up and reform your reactants. So when the rates of the forward reaction and the rate of the reverse reaction are equal, that's when you have chemical equilibrium, and that's a super stable condition. Most systems, if you leave them alone, they will eventually reach equilibrium because all nature, all reactions want to be stable, and equilibrium is a very stable situation. One of the most important and useful applications of equilibrium reactions is Le Chatelier's principle. Le Chatelier's principle states that if a stress is applied to a system at equilibrium, the system will shift to relieve the stress. So it acts sort of like a balance. If you could just imagine, when I read that, I think about, for example, if you were to, I don't know, slam your hand in your locker, that would obviously hurt. So you would very quickly respond by pulling your hand away. So you would shift or move your hand to relieve the stress. That's sort of what's going on here. The system, if you impose some sort of stress on it, it's going to try to fix it back so that it's stable again. Now, there's three stresses that we can impose on a chemical equilibrium. We can change the concentration, we can change the temperature, we can change the pressure, but with gases only. Also remember, this is something to note, if you have a pure solid or a pure liquid, they will never shift the equilibrium. So let's talk about Le Chatelier's principle. I apologize, y'all. If you add to one side of your reaction, if you add extra reactant or extra product, the reaction will shift away from the added component. Same thing if you're adding temperature. If you're adding heat, it will shift away from the side you added heat to. If you remove from one side of the reaction will shift towards the removed component. So it's going to try to put it back where you took it away from. Now let's look at an example. Hopefully this will make more sense. I know on your fill-in sheets it says write the KEQ. We're going to come back and do this at a different time once I've talked about the equilibrium expression. But for now, let's apply Le Chatelier's principle. Notice we have an aqueous substance here, a gas, an aqueous substance, and heat. Now, since the heat is on the product side here, we interpret that as being exothermic. And that's important to take note of. So the question says, how will the equilibrium change if you impose these changes to it? So the question wants you to answer, will it shift to the left, which is the reactant side, or will it shift to the products to relieve the stress? So the first choice says if you add some A. So look at where A is. A is on the reactant side. So if I add some A here, Le Chatelier's principle says it's going to shift away from the added component, meaning it's going to shift to the opposite side of the reaction. So if I add some A to this reaction, since A is a reactant, it will shift to the products. Or you can just say shift right, because that's the side the products are on. The next choice says if you remove some B. Well, B is a gas, so if I come in here and I were to remove or take out the B, if I take it out, well, it was at equilibrium before I started, so it was balanced, it was very stable. So when I come in here and mess up this balance that it has, the system is going to shift and try to put it right back. So it's going to shift towards the removed component. So in this case, it's going to shift to the reactants or to the left. All right, C says if you add some heat, what's going to happen? Which direction will it shift? Well, look where the heat is. Since this is an exothermic reaction, the heat's on the product side. So it's just like if you were to add a reactant or a product over here, it would shift away from the added component. So since I'm adding heat here, it's going to shift away to the opposite side. So if you add heat, it's going to shift to the reactants. Or again, that's to the left. And it will shift until it reestablishes its equilibrium. D says remove heat. Well, if I come in here and I cool it down, I put some ice on it, cool it down, I remove the heat, it's going to try to put the heat back. So that would require that it shifts towards where the heat was so that it could put it back. So if you remove the heat, it's going to shift towards the removed component. So it's going to shift to the products or to the right. Now I want you to try the example on your own that's in your notes. Notice here, y'all, I have a solid and a liquid, and it's important to remember that the solids and the liquids never shift in equilibrium, only aqueous and gases or heat. Again, we're going to do the KEQ later. I'd like for you to do this one. Pause this to give yourself time to try it on your own, and then look at the answer. I'm going to go on because I have a very short time to do this video before it will cut me off. So, lowering the temperature. Well, for this one, look where the temperature is. It's on the reactant side, so this is an endothermic reaction. So if you lower the temperature, that means you're removing the heat. So it's going to shift to the reactants and put it back. Increasing the pressure. Now, pressure only affects gases. So in this case, you have to look and see where the gases are and how many gases are in the reaction. On the reactant side, there are 0 moles of gas. On the product side, both of these are gases. There's a coefficient 1 here and an understood coefficient 1 here. So there's 2 moles of gas. Gases do not like to be pressurized. So if you increase the pressure, these gases here are going to try to shift to where they have more room. So they're going to shift to where there's the fewest moles of gases. So that will be to the reactants again. Removing hydrogen. Hydrogen's a gas. I'm going to take him out. If I remove, it's going to try to put it right back. So it's going to shift to the products or to the right. Adding water. Y'all, water is a liquid. So you would say no shift because it's a pure liquid. Raising the temperature. So the heat's here. If I add heat, it shifts away from the added component, y'all.